Arie? Yes? Okay. I'd like to invite Arie Haenel to the stage. And Arie is a fantastic security professional researcher at Intel. That's right. By the way, my sister also works at Intel. But that's not what why Arie is here. Arie has been speaking and contributing to B-Sides and other events a lot of the time. I think last time I hung out with you, it was the Blue Hat conference, maybe 2 years ago. So thank you so much for coming to the BSidesTLV stage. And Arie is not alone. He actually has a co-speaker. So this is Julien. Bonjour, Julien. Bravo! Hello. Merci! Thank you so much for joining us. And Julien is also a researcher with Intel. He's with Intel IPAS. Yes. Did I get that right? Intel IPAS. And Intel IPAS is Intel Product Security Team. Intel has been a long-time sponsor of BSidesTLV, so thank you. But this is a talk that stands on its own. And thank you. We also have a clicker for Arie. I just want to tell you one more fact about Julien. Maybe you can guess it from his background. He likes wine tasting. Ooh, very fancy. Here in Tel Aviv, we can offer you gin, vodka, beer, whiskey. We don't have, what? Whatever he said. And Malbec? Okay. And now, let's give a nice, warm, giggly afternoon, humoristic welcome to Arie and Julien. Thank you so much. You went to the last slide. You have to go back, the red one. Okay, you're good. Very interesting. Our slides are reverse engineering themselves. It's very interesting phenomena. Okay.
Spoiler alert. F5, please. Thank you. Hi, Julien.
Hi.
So, let's start. Well, let's start it. I like this little computer. Yes, this badge is run by a microcontroller. It's a small computer with a processor, core, memory, timers, I/O, flash, well, even a display. What's happening when I turn it on? How is it different from more evolved embedded systems? How and where this understanding is essential for us, for you, to assure the security of such systems. That's actually what we are going to discuss today. But first, let's present ourselves. So, my name is Arie Haenel. I'm a principal engineer at Intel, and I'm leading an amazing offensive security research team. I have a little more than 23 years of professional experience in software and security engineering. And on my free time, I'm a lecturer at the Jerusalem College of Technology. Hi, guys.
And hello, I'm Julien Lenoir. I'm also a security researcher at Intel. I have more than 10 years of experience in vulnerability research. I do bug chasing, reverse engineering, exploitation, and all these kind of funny things. And talking about funny things, Arie, shall we play a game today?
Yes, of course, Julien. Yeah, during our coffee breaks, we sometimes play CTFs. Thank you, hi, JCTF. But the CTF is finished, so we need a new game. So for today, Julien, I propose that we play a Battleship war. And we know that there's no better way to learn than playing a game. So the agenda for today, we'll discuss first boot sequences, from the most basic to more evolved ones. Then we'll present U-boot, the U-boot bootloader. And finally, we'll present some new original attacks. So back to our badge. How does it start? Well, at the beginning of the interrupt vector table is found the reset vector. Well, it's a fancy name for just an address, which will point to the first instruction to fetch. And from there, the processor will actually execute some code. In the case of our little badge, this will point to the beginning of the spy flash memory. For our Battleship game, well, I would say it's a raft. There's no security, there's nothing interesting to think here. So it's a really rudimentary game, boot sequence, but it's very, very effective. There's absolutely no delay from the moment we start it, well, it runs this application. But of course, it has some limitations. For example, it can be difficult, or sometimes even almost impossible, to update the image. And that brings us to our second model. So here is our patrol boat. Now we added a stage in the boot sequence. There is a bootloader that is running at the beginning of the execution flow. It is used, for example, in the case of the Arduino-like platform, all the families, or others like the Tiva Launchpad here on the slide, to update the main image easily through serial or USB. In this case, the bootloader is just a small piece of software which resides in a part of the flash, usually at the beginning, but doesn't have to, the flash of the microcontroller. It can write the application, the rest of the application, directly without using any other device like a debugger programmer. And this is really convenient, since changing directly the flash memory would require extra interface and extra wiring. But of course, this has some bad influence on our boot time, since we have some more code that is running before the main application. Sometimes it can be even a long time. Some device takes a few seconds to load. And we still lack any kind of security, because we want to assure that the code that is running in our platform is trusted. But since we can't make sure that the content of the flash is the one that we put, including our bootloader itself, well, we have a challenge here.
Yeah, and before we move to the next model, the destroyer, let's discuss the properties we would like to add. So the most urgent one is some level of resilience. Yeah, indeed, the fact that all the functional code is in the flash is a weak point, because it can get corrupted or changed on purpose. We may also need for more complex system that the nicely integrated microcontroller that Arie showed you previously. For example, the boot sequence should handle some configurations of the SOC. Or it may also be used to initialize peripheral that couldn't run directly at boot without this setup. For example, some I/O, clocks, watchdogs, SD card, USB, or even crypto accelerators. And as I said, of course, we are here to speak about security. In order to achieve these goals, we need to add an element to our system. The most common solution is to use a ROM as an immutable first boot support. It will provide us the root element to achieve our goals. In this model, the first piece of code is stored in and run from the ROM. Its main role is to load the next stage you see on the scheme, found in the flash, the bootloader. It can also be used to recover in case of flash corruption. And in some cases, it may include the minimal set of configuration needed, for example, if you want to boot from a peripheral. And of course, adding another component to our systems comes with a price in the total cost, complexity, and the performance, but this should be worth it. Now let's see how we will use this scheme to create a validated boot sequence. Today, boot systems are more features like recovery possibilities, network capabilities, and many other goodies. Some, as Arie said, are even more complicated than you are seeing now on the scheme. We have moved from a very simple patrol boat to something as complicated as a nuclear carrier.
Oui.
And higher complexity means more code, so higher probability of bugs. In this example, the attack surface increases as code size inflates. Both the boot ROM and the bootloader now comprises protocol stacks such as USB, TCP, or even HTTP or TLS. Yep.
Yeah, we jumped too far, I think.
So first, my bad. I don't know. Which slide number are you?
I'm 10.
You're 10? How is that possible? Did you have a cut?
I'm on the first secure boot. So, well, I'd like to present to you for the first secure boot scheme that we have.
Oh, my bad. My bad.
So the main idea here is that for each stage, we will cryptographically validate the next one before passing the control. The flow will form what is called a chain of trust. Due to the immutability of the ROM, We will consider the boot ROM as the root of trust of this chain. If an attacker would want to disrupt this chain, it would need to replace the ROM, which is a lot more difficult and costly than just reflashing the bootloader or the main image. Or there may be other ways, like finding a vulnerability, but more on that later. So, well, if this is so secure, what can an attacker do? So one example is to intervene in the middle of the process without breaking the verification. Due to the linearity of some flow of operations, it is sometimes possible to achieve what is called a TOC2 attack. TOC2 standing for time of check, time of use. The attacker is switching at the right moment the original and valid image, and just after the validator has finished checking the signature, it replaces the access to the next stage with a rogue image. This is, for example, what was accomplished 2 years ago by 2 researchers on Intel boot guard mechanism. Well, of course, the boot sequence or the boot flow of a modern PC is much more complicated than what we have seen, more complex than what we have here, but this idea is actually valid everywhere. In this case, they showed that an attacker with physical access to the spy flash could intercept the execution flow and actually achieve code execution after the boot guard validates the hash of the initial boot block. By the way, one of them is now working with us.
Okay, so my apologies for that. So as I said before, so like Arie said, we have the boot sequences have complexified a lot, and like what you are seeing now is that some have got now recovery possibilities, network capabilities, and many other things, and as I said, we have moved from a very simple boat, the boat patrol, to the most complex one of our game, which is the nuclear carrier. And as I said, once again, higher complexity means more code and higher probability of bugs. So what I was trying to say here is that we have increased the code size, the attack surface, because we have added a lot of goodies and a significant amount of code to handle complex protocols such as HTTP, USB, or TLS. And this can be a real problem if vulnerabilities are found in those pieces of code inside the ROM, because this would lead to unfixable security issues. And one famous example of this is the Nintendo Switch Fusée Gelée vulnerability, which affects the built-in USB stack of the ROM used for recovery, where a memory corruption allowed to execute unsigned code. So we are displaying now a non-exhaustive list of boot attacks. It's not for you to read them all, it's just so you have in mind that there are many kinds, more than we are discussing today. Well, after this introduction tour of the possible secure boot design and weaknesses, we are now moving to the result of our own vulnerability research we conducted within the team on U-boot. But what is U-boot? Arie, can you please tell us more about this?
With pleasure. So U-boot. Well, U-boot is a very popular open source bootloader used in a huge variety of devices, from Chromebook to game consoles, set-top box to e-readers, network equipment, and tons of IoT devices. Even the SpaceX Dragon cargo spacecraft and the Falcon 9 orbital launch vehicle actually use it in space. It can be used, it is used as a first stage consisting of basic needs for the system, like configuring the memory controllers and SDRAM, but it also can be used as a secondary stage. For example, it is necessary for the multiple steps required to learn the modern operating systems from a variety of devices that must be configured in advance, and many more things. So for a moment, we will switch to a role game. Now let's assume that you have chosen this very solid architecture. Yeah? You have a boot ROM, a bootloader, and a main image. You have extensively reviewed your boot ROM so that it doesn't have any known bugs. It is rock solid and uses crypto only approved by your crypto experts. And well, your security folks tell you all the time not to reinvent the wheel. So you decided to use a mainstream, maintained, and up-to-date third-party bootloader, U-boot. Well, is it enough? Let's understand what is happening under the hood. So U-boot stores actually the images, well, most of the time it's on the flash, into a so-called FIT format, which stands for flattened image tree. Remember the tree. Using this complex format, which we will describe into more details in a moment, U-boot offers functionalities like loading multiple images, well, and of course, what interests us, image signature verification for verified boot. Writing a FIT parser is quite a hard task, both from design and implementation perspective. Well, indeed, the U-boot code needs to handle the parsing complexity before being actually able to check the image signature and later pass the control. So let's be very clear. This parsing of unauthenticated code, or unauthenticated data, is a weak point of this boot flow and an excellent playground for security researchers. And now Julien will guide us inside the internals of the FIT parsing.
Of course I will. So the FIT is composed of two kinds of basic elements, the nodes, which are the containers, and the properties of those nodes, which contain data. This is what we call the tree view. On top of this tree view, U-boot accesses the nodes and properties through a path built using the node hierarchies and property names, just like an operating system would access directories and files. Making this analogy with a file system, we call this the path view. What you see here on the right is the minimal set of nodes a FIT must have to support verified boot. You will notice that a valid FIT is fully contained within a root node, which name must be empty. It must also have a node called images to store the images, the loadable images, and a node called configurations to store, among other things, the metadata used by the signature verification process. Talking about signature verification, let's see now how the first step among three works. In this step, U-boot fetches the signature value from the configuration metadata of the FIT tree. It decrypts the signature using the RSA algorithm and the public key, which is assumed to be stored in a trusted location. And the output is what we call the original hash, which will be used in the next step. In U-boot, only a subset of a FIT file is signed when verified boot is enabled. This is a design choice to allow for flexibility to add new images to an existing FIT without breaking the signature. So this means U-boot has to first figure out which parts of the file are signed. It does that by retrieving the list here in red of nodes to verify. Then it iterates all the nodes of the FIT from the beginning to the end, and whenever a node's path matches one in the list, it is selected. And as it is comparing node's path, this step is working on the path view. And once all the nodes are selected, their content is hashed to produce what we call the computed hash. And finally, this computed hash is compared against the original hash generated in the previous step. And if both are equal, the signature is considered valid, and we can move on to the next step. The final step, number 3, is the loading step. U-boot retrieves from the configuration metadata which signature has previously been verified, as I said, the name of the image it has to load. Then, using the tree view, it locates and loads this image from within the images node of the FIT. So, before we move on, let's take a break and remember a few key points about U-boot's verified boot. So we've seen that the U-boot signature verification process is composed of 3 steps: the signature fetch and the loading image step, number 1 and 3, which are using the tree view, and the compute and compare step, number 2, which is using the path view. We've also seen that the feed format is flexible, meaning anyone can add images and configuration to an existing feed tree without altering the signature, as long as the existing pieces of data are not altered, and this is by design. We've seen that U-Boot is working on different views or different somehow abstraction layers, meaning tree view versus path view, and we'll see later that this induces discrepancies. And Arie will now dive into this in more details because we all know that the devil is in the details.
And now, we are happy to publicly present for the first time our evil V-boot attacks. The first one is called permissive name equality. So, in order to execute the signature verification, U-Boot searches for image names and corresponding configurations. It is compiling the names of the nodes in the different places, but not in a consistent way. The path view uses a strict comparison. Well, in fact, this is just a mem-compare. The tree view, on the other hand, is using a model using the @ sign, commonly known in Israel as strudel, to support another model called a device tree node unit address. On the right, you can see what happens when we use a tree view comparison function. The interesting one is the last one. If a node doesn't have the strudel sign, it will be considered equal to the same name postfix with a string starting with a strudel. This discrepancy between the two views is what lets us mount this attack. So for this attack, we add to the feed table an entry, a node for a secondary image. As Julien explained earlier, the format allows to add a new section, so far, no damage done. But our new image is called using the same name as the original one, but we just concatenated a string starting with a strudel, like this @something or @fake. Let's see how the U-Boot code will behave when checking the signature of the valid partition. So, on step 1, the signature blob is fetched from the configurations entry. This uses the tree view method. But, well, this is not important because we have only one entry there. Yeah. Sorry. Yes, sorry. On step 2, the hash of the image to be validated is calculated. Well, this is done using the path view method, which is strict and matching the valid image. So, of course, the signature check will pass, right? But on step 3, the tree view method is used again. And so our fake node, using the same name with the HTML @sign string at the end, will be used in place of the valid one. So what happened? Well, we just bypassed actually the secure code, and U-Boot will pass control to our arbitrary code. Here's the kernel 1 fake in this case. And so we just hit pretty hard the U-Boot submarine. Thank you. That will be enough, right? But, well, since we are already here, and Julien made all the way to here, so we have another one to show.
Yes, Arie, actually, it's never enough. So yeah, here we are again, taking advantage of one of the discrepancies between the signature verification steps. So the feed format specification describes the feed as being contained in one big node, the root node, which name must be empty. The tree view in step 1 and 3 assumes this to be true, regardless, and thus uses the first node of the feed as a root, regardless of its name. On the other hand, the second step of the verified boot checks this explicitly as it works on the path view. But what happens if we build a feed file, as you see on the right, with 2 root nodes instead of 1? Well, this is exactly the idea behind the fake root node attack. So here, an attacker is altering a signed firmware by inserting its own code in it. The attacker is duplicating what we call the genuine root node, meaning the node that contains the whole original firmware with valid signature, but with slight modifications. So the duplicated node we see here in orange, and we call fake root, is put in the feed file before the genuine root node here in gray. The only differences between the two are the new node has a non-empty name, in this example, fake root, and the loadable image it contains is replaced by an arbitrary attacker-controlled one. And let us see now what is the impact on the verified boot process. So during step 2, are you okay, Arie?
Yes.
So, okay. During step 2, U-boot iterates on every node of the file, trying to match each node path with one in the list of the nodes to verify. Because the fake root node has a non-empty name, none of its nodes will match, since their path will begin with the word fake root. In other words, it is completely ignored by the compute and compare step. On the other hand, the genuine content will match, but this is okay because its content was left untouched. So the computed signature is valid. U-boot considers the signature as valid. Later, step 3. Later, step 3 will search for the image to load, as it works on the tree view. It fetches the image to load from the first node of the tree, assumed to be the root node, regardless of its name. It loads the image from the fake root node, thus loading attacker control data, and our submarine is hit again. And well, now our submarine is hit and sunk. Indeed, we've showed 2 distinct ways of inserting arbitrary code to assign image which gets executed, even with verified boot enabled. The impact can be significant. You can imagine, for example, a game console for which the protection then would be broken. An attacker would be able to run arbitrary code and run pirated games, thus breaking vendors' business model, and that's just an example. And well, Arie, I'm afraid that our game is over now.
Yeah, Julien, I think that we can say it's game over. Well, let's draw some conclusion. As we have seen, security engineering, well, it's hard. It is primordial to be safe on the first try on parts that can't be updated later, like the boot ROM. And as any chain, a chain of trust is as strong as its weakest link. And also, we want to remove any NAD attack surface. Well, I didn't draw you for that, because you knew all that before. But even when you did everything right on your code, you have a strong architecture, you reviewed your code thoroughly, you fuzzed it, sometimes you may find it's not enough, because the weakest link is coming from third-party code. For some psychological reasons, we tend to give more credit to third-party libraries than some deserve. We have seen that again and again recently, and not especially on this really great bootloader. Also, pay attention that the vulnerabilities we have discovered here were based on logic bugs. That means that the way to exploit them doesn't lead to any sort of code or memory corruption. So they are not usually discovered by automatic methods like static analysis or advanced fuzzing. And furthermore, they are not mitigated even by the most evolved mitigation techniques. So there is good news here. We will need you, all of you, to actually secure the world. Also, we would like to take this opportunity to thank the Thanks team, Tom Rini and Simon Glass. It was a pleasure to work with you guys on the disclosure and on the fixes. So, well, I have a quick legal note. I think that it is related to Karen's sister. She's on legal at Intel. And the credits for the authors of the licensed pictures that we have used in this presentation. Thank you all for your attention.
Thank you so much, Arie. Thank you, merci, Julien. So this was awesome. I learned a lot of things. I also learned that you get a lot of applause in the middle of your presentation when you do cool things. And the people of B-Sides surely appreciate it. So let's give them one more round of applause. Thank you, Arie. Thank you, Julien. And now I have to announce
some questions.
Q&A. Okay, we're going to do a couple minutes Q&A. Do we have questions for Julien and Arie? Arie and Julien, we have here. Hey, I see your face. Put your mask on. Mask on. Okay. Questions? All right. Control. Please give us the handheld microphone. 1, 2. Check. 1, 2. On the mic. I can do some rapping in the meantime.
Hey, 1, 2.
Okay.
1, 2. Yeah. Okay.
Yes.
Yeah, I understand the logic bug of the tree versus the path view, but why did the path view choose the fake node and the fake argument with the strudel, but not the other one first? How did you make him choose the? How did you make the tree view select the fake one instead of the real one?
Okay, so what is going on there is that you have this format that is called the unit address, like I said. And it is using this strudel. For example, you have kernel strudel 1. Now, kernel and kernel strudel 1 are actually the same. So on the project, the first project that we have seen this issue, they were using just kernel. If they would have used kernel strudel something, so this attack would not have been possible. But since they were just ignoring the strudel part, so it was just, let's say, kernel, so we could make this attack. Because the code was written in a way that if you don't have anything, or you have something with strudel, it will be the same. If they would have called it kernel 1, then the attack wouldn't have worked. Does that answer the questions? I'm sorry, I can't hear you. Yes. Yeah, so if you want just what happens on the second project that we have looked at, they were using actually this kernel at 1 format. So this attack didn't work. But we said, okay, it's not possible that we can't find another one that will work everywhere. So Julien just dig a little more and found the second attack.
Did you check all the versions of Uber till now?
Okay,
does it affect
so
all the backward?
Understand? So the question is that if we have checked everything, so we haven't checked every version, but according actually to the authors, when we discovered that, I think it was in November or December, something like that, Julien?
Yeah, I think it was in December.
So we looked at
November, but the official communication was in December with the maintainers.
So we were in contact with the Danks team, and they said that yes, for a very, very, very long time, we still went back to 2013 or 2015, and all the versions were actually vulnerable. It has been fixed in a patch, so where we publicly released it, or they publicly released it in April.
In March, I think it was in March.
It was on April. Yeah, it was in March, but the version is the release candidate 2 of April, if I'm not wrong, right? Something like that.
Okay, I might have missed it, but excuse me. Okay, so what made it, when you said that the code with kernel strudel run and not the one without the strudel, what in the code of the bootloader made it run the one with the strudel? Is it, what does it select based, I don't know how to explain.
Julien, you want to take this question? I'm not sure that I understood.
I can. I'm not sure I fully understand the question. But so the question is, how makes this select this one? So basically, as we explained, you can insert images, okay, images inside the images node without breaking the signature. So if there is, for example, one is searching for kernel, and then before this one you insert kernel at something, as the comparison will match as the first one, it will pick up the first one that matches, basically.
Okay, first match, okay.
Yeah, the first match. Does it answer the, okay.
Any other questions?
Here on the first row.
So there is going to be some release or some POCs that you are going to release, or it's going to be staying, like it's going, I can find some additional nodes somewhere?
Yeah,
okay.
yeah. So
yeah, Julien.
Yeah, basically we send to the developer everything, even a POC to reproduce the issues, and the POC have been pushed to their repositories as non-regression tests. So if you want to play with this, there's a Python script on the U-Boot repositories, and normally in the Git commits you can grab with the CVs, because we asked them to put the CVs in the commits, so it's easier for security researchers to search for that.
So
Thank
everything
you.
is public. Thank you.
All right, all right, all right. Thank you so much, Arie. Thank you, Julien.